everyone, welcome to the week 7 of the problem solving session for fundamental semiconductor devices NOC 24E02 hosted by NPTEL. My name is Amit. I am a PhD student at ISC Bangalore. So in the previous sessions, what we had talked about started the classification of materials in terms of their electrical conductivity sigma. We saw what are metals, what are insulators, and a unique class of materials called semiconductors. They are unique in the sense that their electrical conductivity can be tuned as per the requirement. And what we also saw is the peculiarity of the semiconductors is something called the band gap. That happens when, let's say, you bring a huge amount of atoms close together and their orbitals overlap, and what you see, rather than having distinct energy states, they split into bands of energy states. So these are still energy states, but they are so close together they appear as if continuum, and we distinctly see a gap between these two bands. So above EC, electrons can be there, below EV, electrons can be there, but in between there can be no electrons. This is the forbidden energy gap. And if you shine, and what can happen is that electron can jump from valence band to conduction band or vice versa, depending on, so here from jumping conduction to valence band, a photon can be emitted, which was the principle for the LEDs, as we saw in a couple of problems. Then what we saw is that this is in energy versus space, E versus X. If I draw another nomenclature, E versus K, this is called the band structure. E versus X is the band diagram, E versus K is the band structure. What we see is that now the energy states can be represented something like this. So this is a parabola, this is the conduction band, and similarly we can also draw the valence band over here. So again, this is the gap, the forbidden energy gap that we had talked about. K is the wave vector, which is 2 pi by lambda. Okay, and this curvature that you see over in the conduction and valence bands, this gives the effective mass of electrons for conduction bands, and for holes, if you take the curvature, you find out the curvature of the of this valence band over here. This is related to the effective mass, which is an important entity in the sense that we know that the electrons are not traveling. Electrons are traveling in the lattice, that they're not free. So they are subject to a periodic potential as given by the Ronig-Penny model. This is potential V versus X. They're subject to this potential, and the quantum mechanical effects will come into the picture. However, we do not want to incorporate them into our discussions, into our numericals every time. So what we do is that we condense all the quantum mechanical effects to one single entity called the effective mass, denoted as M star or M effective, which is related to the curvature in the EK diagram. And then we saw what are so as I was talking, these are the energy states that I have been talking about, right? And so what we saw was that there is a density of states that is given by this function dE, that is how many energy states per unit area per unit volume, right? So essentially there are some energy states in the conduction band, let's say, where electrons can occupy, and this was what we saw is directly proportional to square root of the energy. This is for the 3D system. And how many electrons will occupy this? This was given by the another function called the Fermi function, which was of this form, exponential E minus EF over KT, where EF was the Fermi level. Fermi level is essentially where probability of finding the electron is half at any given temperature. So as you can clearly see, if the energy is more than EF, if energy is more than EF Fermi level, then this exponent will be, this power will be greater than 1, and this exponential will be less than half. So we saw that in terms that it looks something like this. So this is Fe versus E, and this was the midpoint where Fe versus E, and this was the midpoint where the this is the probability of finding the electron at energies greater than E is less than half, which you can see this is Fe equal to half. So we had seen that. And finally, if we simply integrate the total number of electrons, let's say given by n, you integrate from EC to infinity, from EC here to infinity. If I simply integrate that, then integrate dE Fe dE. If you integrate that, we got a good expression for given by something called NC exponent of EF minus EC over KT. Similarly, we found it for holes. So this is the carrier concentration at equilibrium. Remember that we are not applying any any bias as of now. Okay, and this NC was called the effective density of states. um, Finally we can see that now this is just the intrinsic, that is you have not doped it. However, we can dope these materials also. What are dopants? That we saw there are two types of dopants, acceptors and donors. So for instance, donor level will lie very close to, good donor level will lie close to the conduction band, so that electrons can be readily contributed by this even at room temperature, right? Similarly, we saw that the acceptors, good acceptors will lie close to valence band, so the electrons can jump from here to here and the whole contribution can be there. Holes can contribute now to the current that is flowing. And we see something called the incomplete ionization, where these cannot be, with these, even though we have doped them, they need to be ionized. So we need, so below 100 Kelvin what we saw is a carrier freeze out, and if you go to very high temperature, let's say 800 900 Kelvin, even the intrinsic bonds, let's say of silicon, will start to break, and you will have a huge influx of your you will have a huge influx of the of electrons and holes. Electron holes pair will be generated, right? So we had seen all that. In the week 3 we talked, we based on this knowledge we had talked about called the Ohm's law. We are familiar with V equal to IR. We saw another form, J equal to sigma E. J is the current density, E is the electric field, and we saw how the currents, how the charge carriers, let's say, can drift in that. So we saw this formula, Vd equal to mu E, given more Vd, E is the electric field. We saw something like this. So in the linear region, in the low field region, drift velocity is directly proportional to your electric field, which is the proportionality constant is the mobility, right? And we saw that these and sigma, the conductivity was given by Ne nu, for instance for an n-type semiconductor. We saw the different scattering mechanism. For instance, when these electrons are traveling, they'll get scattered by the lattice ions, which the dopants, for instance, and also they'll get scattered by the phonons, which is essentially the vibrations in the lattice ions. Second way the mobile carriers can flow is due to concentration gradient. The concentration is high on one side, low on the other side. And finally, what we see in a non-uniformly doped semiconductor at equilibrium, we saw that the band diagrams may look something like this. EC, this is EV, and this was, let's say, the Fermi level, right? And here we saw an expression called the Einstein relation, d by mu equal to kt by mu. D is the diffusion constant, mu is the mobility, and the other two mechanisms for generation and recombination, which can change the carrier density. Now then we saw in the week 4 the very basic device called the p-n junction, where we saw we bring the p-type material and an n-type material join. This is what the metallurgical junction. We saw different flavors like pn, where p on one side, n on another side, pin, in this an intrinsic material sandwich between the two. P plus denotes high concentration of dopants on high concentration acceptors on p side, while moderate doping on the n side. We saw how does it look like when you bring them close at equilibrium. It looks something like this. So this was the depletion region that we had seen, and we can see the dopant ions were frozen inside this, which gives rise to electric field. The depletion width was existing because the electrons diffused from the n side to the p side and recombined on the p side, which gave to this depletion region without any charge carriers. And if there is an electric field, there will be a potential, which you call the built-in potential. Then we forward bias in the sense that p was connected to the positive terminal of the battery, and what we saw was that this Fermi level, which is flat in equilibrium, split into EFP and EFN because we had injected some carriers. These carriers diffused, the built-in potential reduced, and these carriers could diffuse to the other side, which gave rise to the currents. We also saw the law of the junctions, which was NP equal to Ni squared e to the power QVA over KT, where VA is the applied potential. Finally, we saw in the reverse bias where interesting things happened, and there will be minimal current that was flowing inside there called the reverse saturation current. However, the total current J, the total current density, was given by J equal to JS QVA by KT minus 1. This is the total current through a p-n junction diode. We discussed reverse breakdown in more detail in the avalanche, in which for instance, this avalanche used to happen, for instance, when the dopings are moderate level and the electrons have to travel a huge distance in the depletion region. Please remember that when it's biased in depletion region, so reverse bias, sorry, the depletion region gets widened. So electron, if somehow enters this depletion region, it has to travel across. It can gain sufficient energy that can knock out other electrons, which can further knock out another series of electrons. This chain reaction, the huge amount of current can flow. Avalanche. Zener used to happen. Zener we saw in the case of where we had a high doped p n side, p plus n plus junctions, right? And another example of high dope was the tunnel diode. If you recall, the IV characteristics used to look something like this. The first current increased due to tunneling, band to band tunneling, that is, then tunneling reduced, so the current also reduced, and finally later the typical PN junction drift mechanism kicked in. The other devices we saw were LED, photodetector, and solar cell, which we saw in terms of we will come to this LEDs, photodetector, solar cell, maybe a couple of videos later. I versus V, we saw LED was in first quadrant, photodetector was in third, solar cell was in fourth. And another type of junction that we saw, the Schottky diode, which is essentially a metal semiconductor junction. We saw two terms called the work function, which is the energy required to liberate an electron from Fermi level to the vacuum level. Electron affinity is from EC to the vacuum level. We saw two types of contact, namely rectifying and non-rectifying contacts, and the mechanism in Schottky diode was the thermionic emission. Then we moved to a third three-terminal device called the bipolar junction transistor. Two flavors that we had in the last session saw NPN and PNP, and we saw that how does the doping and width of the three junctions, emitter, base, and collector, are important in order to have an efficient working of BJT. Then we saw there are four modes of biasing a BJT. So so essentially, if you recall, because there is an electric so let's say I'm talking about NPN BJT. So there is an emitter base and there is an emitter collector. So you can, this is forward reverse, reverse forward, and reverse. So the four combinations, and we saw the forward active mode, reverse active mode, saturation, and cutoff. We saw all these modes, right? All these operation regions based on just on the biasing of emitter base junction and the base collector junction. And we studied, we discussed the working of a BJT extensively for the forward active mode. The four terms which came into the picture: emitter injection efficiency, that is essentially that how much so in a forward active mode, so the diagram used to look something like this. So this is your emitter, this is your base, this is your collector, this is the depletion region, emitter base, and this is the base collector depletion region. So so here the electrons will be will diffuse across the p side. A very small amount will recombine here. So emitter injection efficiency was essentially your how many number of electrons, the ratio of electron current to the whole current across this p-n junction of emitter base. Base transport factor is how much of the electrons that are being injected into the base are recombining, because remember this is a p-type dope, and that's why we keep the doping of base low. Finally, we saw the current gain, which is given by beta, which is essentially your IC over IB. So these are the various terms. We solved a couple of numericals on that. So now this time so if you recall, I had talked about transistors, right, extensively, that the transistor is a device in which a third terminal is used to control the flow of current between two other terminals. I also introduced another type of transistors called the FETs, field effect transistors, and a very common FET is MOSFET, Metal Oxide Semiconductor Field Effect Transistor. Okay, but in order to understand how a MOSFET works, we need to first spend some time, that is this lecture, this session, on understanding how a MOSCAP works. So if you understand how a MOSCAP works, it's relatively just one step forward in understanding how a MOSFET works. This is similar to understanding we first talked about the PN junction, right, and then only we talked about the NPN. Okay, so let's just first understand how does a MOSCAP work, then we'll increase the complexity a bit in the next session to understand the working, the fabrication, and the working of a MOSFET. So today I'll be talking about the MOS capacitor, Metal Oxide Semiconductor Capacitor. So you have a metal, you see in the black over here, right, and then we have the oxide. This oxide is an insulator. Okay, so for instance these devices, and finally we have the semiconductor, the substrate, or semiconductor substrate. Let's say for this discussion I'll take it to be silicon. So what type of insulator we are talking about? Fortunately, we have a very good oxide on silicon, which is SiO2, hence you see this term oxide. So typically this is an MOS stack, but a more general way of seeing it is metal insulator semiconductor. So if you encounter MIS, more often than not in context of silicon, it will be MOS. Okay, so just don't, there's no need for confusion. Metal oxide semiconductor is a subset of metal insulator semiconductor. Okay, and you can see various other parameters, like these are the two terminal devices. So for instance, you can apply, so for instance, usually what we do is we ground the semiconductor terminal, right, and you can clearly understand it will be a Schottky contact here, because this wire has to be, you see this black dot over here, this is a Schottky contact essentially. And how do we see two types of Schottky contacts, rectifying and non-rectifying, if you recall. Okay, so and the other terminal is here, which we use, which I will be referring to as gate or G. Okay, so this is the terminology that I'll be using throughout this session. Please remember, this gate is essentially something, a gate, as you typically know, is something to regulate. Gate regulates the flow of anything, right? A gate regulates how many students can come into the lecture hall and so on. So here there is no regulating because there's only one terminal. But we'll when we extend it to MOSFET, the same MOS capacitor, then you'll be able to appreciate why I'm calling this terminal gate. But for just time being, just assume some terminal G. Okay. So and I'll make some assumptions, right? What I'm talking about here is an ideal MOS capacitor, ideal MOSCAP. So what are these assumptions? That metal and semiconductor Fermi levels are same. Please remember, there we have a metal on this side, then an insulator, and then a semiconductor. So each of them will have a Fermi level corresponding to some vacuum level, right? And here I am assuming that they are the same. Please remember, they need not be the same. Okay. That is, if you remember the work function phi f. So I am assuming here, I'll write it here itself. Just a second. So I'll write it here, that phi m equal to phi s, rather, not phi fm. Phi m, because work function already takes into account that we are talking from the Fermi level itself. Okay. So I'm talking about phi m equal to phi s. So this is the assumption. Unless the problem states otherwise, we'll assume this is true. Second big assumption we are taking is that no traps at semiconductor oxide interface. You see this interface over here, this interface, oxide semiconductor interface. We are assuming it's a pristine interface. That is, there are no traps, so no electrons can reside here, etc. And also this oxide is perfect. That means it's SiO2. No defects or anything. These are two very big assumptions, and we'll break first of these two assumptions. Okay. Third is that the metal is thick enough that we'll call it an equipotential surface. The metal, I mean, I'm talking about here. But this means essentially is that the electric field is uniform across the oxide, and even the electric field that will penetrate into the semiconductor substrate. Okay. Fourth assumption is that the semiconductor thickness, you see this semiconductor thickness, let's call this T silicon, is larger than maximum depletion region thickness. So this is the depletion region, W, which is denoted in gray. So as depicted in this schematic, that thickness of silicon is more than the depletion region. This is more often than not true, because the depletion widths that we typically encounter are a few microns at the maximum, and the silicon that we typically have is tens of or even hundreds of microns of silicon. So this is a very safe assumption. And finally, I had hinted on this, that oxide is a perfect insulator. That is, there is no leakage path that is available. So the electrons that are there, only the electric field lines will be there inside the oxide. As such, no electrons can flow, or holes for that matter, can flow between the gate and the semiconductor substrate. So there will be no current flowing through this device. And just contrast this with the capacitor that you are habitual of seeing, something like this. You ground this terminal and call this terminal G. No current flows through that, right? In equilibrium, in steady state, right? No current in equilibrium. No current is flowing through this in steady state, rather, because you are applying some Vg. So similar thing is happening here. So this is so this is till now I've just talked about that what is a MOS capacitor, how does it look like, what are the different layers, and some assumptions. We are going to break a couple of these assumptions towards the end of today's session, but throughout, otherwise, unless I state otherwise, this continues to be true. Okay, now let's build up on this knowledge and try to understand its working. Now please note that we have only one thing in our control, which is the gate. right? When you have fabricated, let's say you know what is the epsilon of the dielectric constant of this oxide, the thickness of this oxide, for instance, the doping of the semiconductor, so on and so forth. Okay, right? So till now, I have said that we have the semiconductor substrate. I have not talked about whether it's a p type or it's n type. Okay, this is the question which talks about that, right? This is just the nomenclature, so just don't worry about these terms called the inversion charge. What are they? What are they not? Okay, so I'm just, because I'm just introducing, I'll build it up gradually. Okay, so there are two, as you can see, depending on how the semiconductor is doped, you can have two kinds of MOSCAPs. Okay, so MOSCAPs can be of two type, N MOSCAP or P MOSCAP. Okay, we have to identify what is the definition in N MOSCAP. Okay, electrons are in inversion layer, and in PMOS, holes are in inversion layer. Okay, so what is inversion layer? I'll introduce in a bit, but that's the nomenclature. Okay, right. So let's just have a look at the first, or the image on your left. Let's try to identify the three different, so this is your metal, the dashed material shown, this is your oxide, and this is your semiconductor, and this is your EC, this is your EI, the intrinsic level, this is your EF, this is the EV. Forget about whatever is happening, why the bends are bent and so on, and let's just not worry about that for now. Okay, so what I can clearly see, for instance, here, that EF in the bulk, so you can see the bends are bending, there's some depletion region. Let's just not worry about that. Forget about this. Look here, EF is close to EV. This means it's a p-type semiconductor. This semiconductor is p-type. Okay, and p-type, this means in the bulk, whole majority in bulk. If the majority is whole in bulk, in the inversion layer, it will be opposite of this. In inversion, yeah, let's say after inversion, electron majority at surface. I'll go into these terms a bit more detail, that what does inversion even mean. After I'm using this term inversion, but as you can see, the inversion literally means whatever is there, you flip it. So for instance, you expect a p-type semiconductor to have whole as majority charge carriers. However, after an event called inversion, the electrons form the majority at the surface. By surface, I mean this interface. I should not say surface, I'll rather say oxide silicon interface. Okay, so if you are given a p-type substrate, right, then you will form an NMOS, and the definition of NMOS is that electrons are in the inversion layer. Okay, so we see NMOS devices have electrons as inversion charge. This is correct. Similarly, you see this again, this is your metal oxide, this is the interface, the oxide semiconductor interface, and this is the shear semiconductor, and you have this depletion width W over here. Again, EC, EF, EI, and EV. We see EC is closer to EF is closer to EC. This means this is an N-type semiconductor in the bulk. This means electron majority in bulk. After inversion, what is inversion? I'll come to that in the next slide. After inversion, there will be a whole majority, means if the electron majority is there in the bulk, now after inversion it will be whole majority at interface, at oxide semiconductor interface, this interface over here. Okay, so what we see is that PMOS devices have holes as inversion charge. And this question has more than one option correct, so as I have been saying multiple times, please be careful while attempting these questions. Okay, so this is just the definition. So NMOS devices means NMOS devices will be made on p-type semiconductor. Okay, Now for our discussion, I'll be explaining it at every point of time. Okay, so what we have, the first region that we have is what is known as the flat band. Okay, flat band, as the name suggests, the bands remain flat, and please understand that I'm not applying any bias over here, so naturally the system is at equilibrium. Okay, and the EF will be constant throughout, so I'm not shown EF here on the metal side, but it will be the same, because remember we have assumed phi m equal to phi s, so whatever the vacuum level is over here, E vacuum, right, Fermi level will be same throughout in the metal as well. That's why you see no bends or bending, because the electrons have now electronic energy on the semiconductor side as well as the metal side is the same. Okay, just to clarify, this is metal, this dashed line, this is semiconductor. You see this semiconductor EF is close to EV, so this is a p-type semiconductor. Now you can get a hint, as I told, the p-type semiconductor, p-type substrate will give rise to NMOS type devices. Now we'll see how they do that actually. So this condition is known as flat band, where not applying any gate bias. And please remember, in this circuit I am grounding the other terminal. This means the substrate semiconductor terminal is grounded. All right. Now let's apply a bias Vg less than 0. Let me just, for the sake of completion, let me just draw that. So this is metal, this is gate terminal G, oxide, and p-type semiconductor. I have grounded this. Okay, this side has been grounded. Now what we do is we apply a small Vg, some voltage Vg negative. So now what's going to happen, you can simply assume, see again, no current can flow through that, but electric field lines can still penetrate. So if you apply negative potential to this, it will repel the holes that are here. Sorry, it will attract the holes. Negative potential you're applying, it will attract the holes. So what's going to happen that is that now holes, you can see what's going to happen as compared to the bulk. This is the bulk region over here. Let's say this is the bulk, and I'm calling this region as surface. Okay, calling this region as a surface. This, why calling it surface? Essentially it's an oxide semiconductor interface, which I interchangeably be calling as surface. Okay, so what's happening here, you can see EF is closer to EV over here. In the bulk there's still some distance, and EF is closer to EV, right? Now if you recall the concentration of holes, so if EV minus EF decreases, the concentration of holes will increase. It's given by this expression, right? So in this accumulation, that's why it's called accumulation. So this means whatever the concentration is here in the bulk, since EV minus EF has increased, EV minus EF increases at surface, this implies holes increase, and this phenomena is also known as accumulation. You are accumulating the holes, you are collecting the holes which are there inside this semiconductor. Okay, now let's do the now let's flip the bias. Now we will apply a bias which is positive. Okay, now as you can clearly see, if you apply a positive bias, the holes will be repelled, electric field lines will penetrate here and the holes will be repelled. So thus you will see depletion forming. Now you see forming of depletion, the holes will be repelled. So what will be left behind? The lattice ions, the acceptor ions that you have that you have put, right, if the holes are repelled away. Okay, so so we'll see that now. Excuse me. Yeah, so what we see is some depletion charge that will appear here, as a negative depletion charge rather. Okay, and this process this process we had talked about this in detail. This is the depletion is forming, depletion region is forming here, and but you can also clearly see the concentration of holes will keep on reducing, because essentially they're being refilled away, again using this expression. So EV minus EF, you see EV minus EF is increasing. What I'll do is I'll remove for the time being these charges. Okay, they're still there. Sorry, so I'll just put a few of them here. That's it, to denote that the lattice ions are here. So what you see in this depletion region, EV minus EF, this is EV, So what you can see is that EV minus EF is increasing. EV minus EF is increasing gradually, right? Sorry, EV, yeah. So it's EV minus EF. This term is becoming more negative, right? Because EF is larger, EV minus EF is becoming more negative. What this means essentially is that the hole concentration is reducing, which makes sense because that's what I'm saying, that the holes are being repelled away due to this positive potential that you're applying on the gate, right? So this region is called depletion. And now what you can see, a peculiar thing has happened. Let's say you apply such a potential that EF at surface is equal to EI at surface. So this is what I mean by surface, this interface. Okay, EF at surface is EI at surface. This implies concentration of holes will be nothing but Ni. This means in this state you have applied such a Vg that if the Fermi level is coinciding with the coinciding with the intrinsic level, what you have EF directly at the mid gap, right? You can see in the surface the EF is directly at the mid gap between EC and EV. So this means now this material which was P type, now it has become intrinsic. What will happen if I increase the bias even further? Let's do that. If I increase the bias even further, but you can see that EF is now at the surface. So you see depletion region has increased a bit more, right? Depletion width. This is the surface I'm talking about. But you can see is that EF at the surface is now closer to EC. But this means again, I'll write this expression and C exponent of EF minus EC over KT. The material here was P type in bulk. At the surface, you can see EF is closer to EC, and this entity will be greater than the entity P because the expression is this. At surface, material is N-rich, electron rich, while in bulk.
Sorry to disturb you,
Yeah.
but we are talking about the P type only, no?
Sorry?
So far we are talking about the P type.
P type.
Now,
yeah.
We are talking about the N type.
No. We're still talking about the P type. So look at this material. The material in the bulk, EF is still closer to EV. Correct? Look
Yes.
at this region. EF is still closer to EV. I'm just rotating the knob here. The gate potential is what I'm changing. And that's it. I'm not changing the material. I'm just changing the potential that I'm applying at the gate terminal. That's it. So if
but why the expression as N?
The N and P is still there. This expression is still here.
Okay.
It's not that it has vanished. This expression is still valid here. The reason I'm writing that here, because in this expression EF minus EC is a huge number. You see this much, right? In the accumulation plot, EF minus EC will be very close to the band gap here, right? So this quantity will be a very negative quantity. Okay, and hence the concentration of electrons here, for instance, in this case, the concentration of electrons will come out to be maybe 10 to the power 4, let's say, and concentration of holes, let's say, comes out to be 10 to the power 19. That's why I'm not even talking about electrons in this case here. In this case, however, if EF is very close to EC, the concentration of electrons now will jump to, let's say, 10 to the power 18. The material system is the same. I'm just changing the gate voltage. What has happened? By changing the gate voltage, the concentration is just 10 to the power 4. Here it's also equal to N. Here it's 10 to the power 10. Has now come to 10 to the power 18. Just by changing the gate potential. I have not done anything else. The material system still remains the same. The electron concentration has changed, increased or by orders of magnitude, and correspondingly the concentration of holes has also decreased at the surface. Please remember, I'm only talking about at the surface. By surface, I mean the oxide semiconductor interface. This, which I'm denoting it right now, where my pointer is. Right? The material system still remains the same. Here also, I can write P equal to NV exponential of EV minus EF over KT. This still remains the same. This has not changed at all. Okay. So, yeah. So let me see. Correct. I think, yeah. So this is what is happening essentially. Why we call it inversion? Because in the bulk, the material is still p-type. You can see EF is still closer to EV, while at the surface, just because you applied a very large positive potential, what you are having is that at surface the material has become p-type, sorry, n-type. At surface material is electron rich, while in bulk it is hole rich. And you can see this phenomena is called inversion. Why does inversion happen? Inversion happen because essentially first you are creating depletion. You are repelling the holes away by applying a positive gate potential. If you still increase the gate potential, what you are going to have is you are going to have an inversion at the oxide semiconductor interface, right? And as we had discussed in the previous problem, that a p-type substrate will have electrons as inversion charge, and this is called an NMOSCAP, NMOS device. So this is a couple of more problems to just illustrate the same thing. Just now we'll have different diagrams now. So as you said, that the material is p-type or n-type, the very first step that you do is identify. So first of all, I'll assume that phi m equal to phi s. So all the assumptions which you saw in the first slide are still valid here. Okay, I'll just assume that that they are still present. Okay, so just a second. Yeah, so let's talk about the material one. So what we need to find is that we need to identify the type of material and what type of device it is. So that's a fairly straightforward question. So we know this is EI, the black dotted line. This is EF. This is EV. EF is closer to EV, so we know this material one is p-type. So material one is not n-type. Material one is p-type, 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 and p-type. Right? And we know p-type materials give rise to electrons as inversion charge, and they can form a n-MOSCAP. P-type material will form n-MOSCAP. So this is wrong. This is correct. This is wrong. This is correct. So now I can have. So this is also wrong. So what we can, so only either this third option or fifth option is correct. Now let's look at this second device. So here we have EF closer to EC in the bulk. This means it's a n-type material, right? It's an n-type material. So all these, only one option is crossed. An n-type material we talked about will can give rise in inversion of holes, inversion layer of holes, which forms a p-MOSCAP device, right? So this option is crossed. This is crossed. So we can have this, or this. So again, 3 or 5, only these two options survive now. 3 and 5 survive. Third material, EF is closer to EV, which means this is a p-type material, and p-type material can give rise to inversion layer of electrons, which we call such devices NMOS. So we have a p-type and NMOS. So this is incorrect, this is correct. So what you have, this option is the correct one. So highlighting in green, so this option. Simply you need to identify the device, the substrate, that the doping of the substrate, which can be given by the EF, where EF lies corresponding to the EC and EV. And if it's a PMOS, if it's a p-type substrate, it can have an inversion layer of electrons. Now I have not talked about that what is the gate bias here, right? We have not talked about that. We are just first of all identifying just the material system. Okay, in the next problem we will try to identify where it is: accumulation, depletion, inversion, and so on. Okay, so again, the first exercise what we'll do is we'll identify the type of material. So this is EF, this is EV. So this we know is a p-type material. Okay, and you see at this surface, this is what I've been referring to as surface. At this surface, EF has become closer to EV. This means it has become even more p-type. In bulk it was p-type, but now it has, in this diagram, it has given even more p-type. Such a thing will happen when you apply negative bias, because this is accumulation of holes, right? So what we are looking at, is the accumulation of holes. this is incorrect, this is incorrect, this is incorrect, this is incorrect. We are looking at accumulation of holes. And when will the holes accumulate? When you will apply negative bias. Simply understanding a negative, if you apply negative bias to a p-type substrate, the holes will get attracted to this interface. So we have is this negative and accumulation. Okay, now let's do the second device here. So we have EC, EF, EV. In the bulk, EF is closer to EC. This means it is an N-type material. An N-type material, you see at the surface, EC has now become even more closer to EF, right? This is the surface. EC has become even more closer to EF. This means electrons have now started accumulating. The concentration of electrons will increase. Please remember this expression. EF minus EC is even smaller here. Okay, EF minus EC is smaller, so N will be higher. So N at surface will be higher. This means electrons are now getting collected over here. So electrons are getting accumulated. So this is wrong, and all these options can be correct. When will the electrons get accumulated? When you apply a positive bias. If you apply a positive bias, the electrons will get attracted to this interface. Okay, so we have to apply a positive bias. So this is incorrect. This can be correct, this can be correct. Okay, in the third case we have, again first we'll identify the type of substrate. So we have EI, EF, EC and EV. EF is closer to EV. This means it's a p-type material. In the bulk it's p-type. At the surface you see, however, EF is closer to EC. This is EC. At the surface, this is the surface I'm talking about. At the surface, EF is closer to EC. This means in bulk p-type, at surface N-type. This phenomena we have talked about is known as inversion. So we are in inversion. This is incorrect, this is incorrect, this is incorrect, this is incorrect. When will the inversion happen? For inversion to happen, depletion has to happen first, right? And when will a p-type substrate deplete? When you will apply a positive potential. If you apply positive potential here, it will repel the holes, depletion. If you keep on increasing this positive bias, you will see the depletion stage will vanish and will start inverting near the surface. So this and this. So option 3, this one. Option 3 will be your correct answer because it has this one. Okay, so this is the way to approach these kinds of problems. Just by looking at the band diagram, you can understand what type of substrate it is. Once you identify the type of substrate, you can now try to see that what regime it's operating in. This is what we are doing in this exercise, right? Just to quickly do this one more time, just to put it in your head what we are talking about. Okay, so first we have EF is close to EV. You can see this implies a p-type material. P-type material means it will give rise to an N MOSCAP. Okay, so p-type material will give rise to an N MOSCAP. So one of these two options will be correct. Fine. So either this or this. In the second device that is given to us, we have, this is EC, this is EF, this is EV. In the bulk, EF is closer to EC. This means it's N-type. N-type materials give rise to PMOS. They can have an inversion layer of holes, which is known as a PMOS device. So N-type and PMOS. So this can be correct, this can be correct, this can be correct, right? Finally, in the device 3, what we have is, choose the color blue. EC is closer to EF, again in the bulk, which means it's an N-type device. If it's an N-type device, it can give rise to a PMOS type of material. So N-type and PMOS again, N-type and PMOS. So what you see is option 4 is the one which satisfies all these conditions. Okay, again this is the same routine that I have done in the previous slide. I'll do it one more time to emphasize as to what I'm talking about. Again, please identify what type of material in the bulk is. EF is closer to EV, so this is a p-type material, right? And what you can see At this surface, the material is intrinsic. Okay, you can see that EF is directly coinciding with EI. This means P type has been done intrinsic. This means holes have vanished. This is the depletion region we are talking about. This is operating in depletion. If you apply a positive bias to the gate, the holes will start being repelled away and it will lose its p-type character. You can see EF is moving close away from EV as you move towards the surface. As you move, look in this direction, EF is moving farther from EV. This means it's losing its p-type character. It's losing its holes. When will it lose the holes? When the holes will be repelled away from the gate. This means you apply positive potential and you have reached the depletion. Not inversion yet, because inversion will happen when EI will dip below EF, which has not happened yet. So this is wrong, 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 this is correct. Okay, in the second device, EF is closer to EC, which means it's N type. In the bulk, let's say what's happening on the surface. On this surface, you see EF is closer to EV. Look at these 3 points, this point, this point, this point. EF is closer to EV at the surface. This means at the surface it has become p-type. In the bulk it is n-type. This is known as inversion. We know that. So this is inversion. But when will that happen? For inversion to happen, first depletion has to happen. Depletion, this is n-type rich material, electron rich material, because remember this is n-type, right? We have donors. If you apply negative potential, the electrons will be first repelled away. You will enter the depletion. If you still apply a more negative potential, even more than that, you will enter the inversion. Hence, the bias that you have to apply here is negative. This one. Finally, for the third one, again you can see it's an n-type material. Why do I say that? Because EF is closer to EC in the bulk. N-type. Right? Let's see what's happening at the surface. At the surface, the material is intrinsic, right? Why would an n-type material become intrinsic? Because you can see EC is become farther from EF, right? When will this happen? If you apply a negative potential, electrons will start getting repelled away and the concentration of electron reduces. Concentration of electron reduces. First, you have to apply negative potential. So all of these options are wrong. And you are still in the depletion because EF has not dipped below EI at the surface. EF has not dipped below EI at the surface. You're still in depletion, not in inversion. This is the correct option. And finally, the last option will be the correct one. So till this point of time, I have discussed, I just have give you a very brief idea as to how to identify the materials and the nature of the devices that we can form on them and in which regime they are operating: accumulation, inversion, depletion. Flatband we have not seen because it's fairly obvious. The bands will be flat as the name suggests. Okay. The second thing which we now will look at with the problems itself is the charge distribution. How will the charge distribution look like? Okay. So let's do that. So again, similar style of problems, right? So we have EF closer to EV in the bulk. So we can say this is a p-type material. Let's look at what's happening at the interface. At the interface, you can see clearly EF is equal to EI, right? EF is closer to EI. When will that happen? This means the holes will be repelled away. You can see the distance between EF and EV has increased as you move from bulk to the surface, right? This means you must have applied a positive potential to the gate. Then only the holes will be repelled away, correct? If you have applied a positive potential to the gate, this means essentially you are putting a plus Q charge. So first of all, you have identified that this is in depletion. All right, fine. What about this device? This is again a p-type device because EF is closer to EV. At the surface, however, EF is closer to EC. This means here it has become n-type. This is known as inversion. When will the inversion happen? Only after depletion. Depletion, you have to apply positive bias. You see this case. You have to apply a positive bias, right? What about this? This is an n-type material. EC is closer to EF. This is n-type in the bulk. What about at the surface? At the surface, EC has become even closer. You can see EC has become even closer to EF. This means it has become even more n-type. Let's say n plus type. What does this mean? Accumulation. When will the accumulation happen? If you apply positive bias, electrons will be attracted to this interface. Correct? So what you have seen in that, in all the three cases, gate will have a plus Q charge. That's why A, B, C have plus Q charge. All right. For option 3, you will have an accumulation of electrons, negative charges. You can see that there will be no depletion, there will be minimal depletion region, which happens to be in option B. In option B, you can see there is no depletion happening. In this option A, this will also have depletion. Inversion comes only after depletion. So 1 and 2 will definitely have depletion, right? So 3 matches with B. So 3 matches with B. So this is the correct option. And we already said this is accumulation, right? This is how the charge distribution of accumulation looks like. Now let's see option A. So this red block that you see is of depletion charge. This green that you see is of accumulation. When do you have accumulation? For option 2. So 2 will match with A, which is the inversion. This is the inversion charge that you are seeing. Sorry, not accumulation, this is the inversion charge in green. Over here you have the gate charge plus Q, and this red you have is simply the depletion charge. So only depletion is in option 1. Depletion charge will be negative, as I told you. If you repel away the holes, then only the acceptors are left behind, which are negative in nature. So that's why you have a negative charge here. It's a depletion charge, which is negative. So option A is the correct one. Okay. So till now we had talked extensively about the class of the materials, how to identify the substrate and what kind of devices can we make on them, and secondly, how do the charge profiles look like in each of these devices for that matter. Okay. So this is just essentially the formal definition of inversion. Okay. So MOSCAP is said to be in inversion when the minority carrier concentration at the surface equals or exceeds the majority carrier concentration. We have seen that. This is the flat band, this is the inversion. So EC, this is EV, this is EC. So what we see is that there is some, what is the whole charge here in the bulk? It will be NV exponent of EV minus EF over KT, right? This is some EV, this entity, right? What will be the, this is, let's say, in bulk. What will the electron concentration at surface over here I'm talking about, and surface, it will be equal to NC exponential of EF minus EC over KT. This gap, you can visually also notice that this gap is the way it's defined is that how should I say this? Yeah, this is how I say. We define two entities now, phi F and phi S. Phi F is nothing, it denotes this. This is phi F. What is phi S? Phi S is the amount of band bending, that is intrinsic level bending. Essentially all the bands will bend equally. EC will bend equal to this phi S, EI will bend equal to this phi S. So this is the extent of band bending. This is the extent of band bending. Phi S denotes how much the band is bending. Phi F denotes essentially your doping. Because remember, it's the difference between EI bulk, which is constant, it will lie at the mid gap of EC and EV. EF will be decided by the doping, right? So essentially phi F denotes how much doping you have. Phi S denotes how much the bends have bent. Okay. So yeah, so we need, so what we formally define is that this entity is sorry, 1 second, I had made an error. This is phi F, okay, EI minus EF, right? And this entity is phi S, because this is the amount of band bending EI has seen, right? So formally the way it's when is the strong inversion is a term that we use. Strong inversion we say when phi s equal to 2 phi f. This is the formal definition, okay, of the band bending of the rather, one second. This is the formal definition that we ascribe to the definition of inversion, that how much, whatever the nature of it was, same nature has now been flipped. Essentially this entity in blue you see will be equal to this entity. So essentially when the nature exactly flips, that's what we call is that strong inversion. So this is the definition, the formal definition, and I've already said inversion when a minority carrier concentration at surface, because it's a p-type material, the electrons will be in the minority. So minority concentration at the surface, this is what we define as surface, equals or exceeds the majority in bulk. Okay, so when n surface is greater than or equal to p bulk, and this is the corresponding energies that we ascribe to that. Okay, yeah, next. So again, to define strong inversion even more formally, right, that how does it vary with the surface potential. Okay, this is how it varies. We've already excuse me, how does the accumulation, depletion and inversion charge profile looks like. We have already seen that in one problem, and this is nothing but your carrier concentration. Okay, this is what we have as a carrier concentration. So in this side you have the accumulation, this curve that you see, yeah, and then if you apply positive potential, you will have some depletion. If you increase the positive potential even further over this, you will have weak inversion. If you increase it even more, you will have strong inversion. And how will the dependence go like? Dependence is exponential. All right, in strong inversion, that dependence is exponential. So we see it increases exponentially. This one. Okay, this might look slightly like advanced, because we do not usually talk about the concentrations of electrons as such. We only talk about the regimes: accumulation, depletion and inversion. Inversion here has been split into two again: weak inversion and strong inversion. And this is for a reason, because if you look at this very carefully, which I would advise you to do, is you see some different parameters that have been used. This is essentially the same thing which we are talking about over and over again. Na is your doping, Ns denotes your electron concentration at surface, again Ps denotes your electronic concentration at whole concentration at surface rather. And so this is the same things that I've been talking about. So for instance, in depletion you see the electrons and holes at the surface are still lower than Na in the bulk. But you see in weak inversion, what is happening, the number of electrons are now greater than number of holes. This means the nature has changed, but it's still weak, because the concentration of electrons on the surface is still not surpassed the bulk hole concentration. But here it has even crossed the bulk hole concentration, which is defined as the strong inversion. So again, different ways of defining the same thing. It helps in the sense that the way you're imagining it. I find it easier. I'll show maybe in the next diagram. Yeah, I find it easier by just remembering using this plot. Okay, here we need to identify what is surface potential. So what will the surface potential for an NMOS device? So an NMOS device, remember, will have a p-type substrate. Okay, of a p-type substrate, if you apply a negative bias, you will attract the holes, you will accumulate the holes. Correct? This is the flat band. If you apply negative bias, you are essentially, so EF, this is the p-type material. EV is closer to EF in the bulk. In the surface, EF has become even more closer to EV. This means hole concentration has increased. When will the hole concentration increase? If you apply negative potential, the holes will get attracted to this interface. This is known as accumulation. So you can see that for negative potential, it will be accumulation, right? If you apply positive potential, you will repel away some of the holes, correct? And you will form a depletion region, because there will be negative charge. The acceptors will be left behind. You'll first enter the depletion. Why know it's depletion? Because we know that the nature at the interface, it's still intrinsic. In the bulk, it's p-type, because EV is closer to EV, but at the surface, it's only intrinsic. It has not, the nature has not flipped yet. This means we're still in depletion. Okay, so that's why we call it. So first, the depletion will come. If you cross 2 phi f, yeah, this is phi f. This entity is phi f, right? And this entity is also phi f. This is when we happen the strong inversion. So this, the total band bending will be phi f plus phi f will be 2 phi f. Okay, so as I was saying, phi s, if it's greater than 2 phi f, that means you have strong inversion, which is what we are talking about here, depletion, and then we'll enter the inversion. So I find it easier to remember it in this way. Phi s is again a surface potential. This interface is what we have referring to as surface. So I find it easier, right, to just remember, to have it in this fashion, right, rather than this diagram where we have, where was it, this electron concentration. I find it a bit difficult because it has much more terms. This is, I find it much more favorable because I know I can study the band diagrams to understand in which regime the MOSCAP is operating in, and finally just by looking at the phi s, first way is to look at the band diagram, second way is to look at the phi s. Just by looking at these two things, I can completely understand as to where my device is being operated. Okay, right. So now we'll be doing more of the numericals in order to have a better understanding rather of the discussion that we have had, because now I have laid the base. Theoretically there's not much left. A couple of things are left actually. Remember that I have told that I'll break those assumptions which I had made of ideal MOSFET capacitor. We'll break it towards the end, and secondly we'll also try to understand the low frequency and the high frequency CV curves. We're talking about capacitance here, right? So if you vary the capacitance, how does the voltage change? Sorry, if you vary the voltage, how does the capacitance change? Yeah. So this problem asks, the capacitance of a MOS capacitor can be represented as a series combination of two capacitors. What are these two capacitors? So let's see, right? This is again just a diagram that I have borrowed. So you have seen this, three regimes. You have seen this already. Let me draw the schematic of the MOSCAP. So this is your metal, this is your oxide, this is a semiconductor, right? Metal oxide, metal or gates, oxide semiconductor. Okay, first capacitor that you see is this. Look at this fellow, right? It has charge on this side. How do I know that? You see this charge in all the three diagrams, we have some charge over here. So this will have some capacitance. We call this Cox. What is the value? Epsilon oxide A by Tox. This thickness is Tox. There will be another capacitance. See this, because there is some charge even here as well. These charges, either this or this or this. I don't know, but there will be some charge inside the there can be some charge rather inside the semiconductor, right? So here in this diagram there is no charge inside the semiconductor. All of this charge is across the oxide. Here that's not the case. Yes, some charge is across the oxide, but some is still inside the semiconductor itself. Remember, this is what we had talked about as the depletion capacitance. If you recall your PN junction session, we have talked about this, right? So what you can see is that, just compared to this diagram now. This is metal or gate. This is Cox. Let's call this C semiconductor. This is the same diagram as this. You have a metal and gate contact, you have a ground contact, you have the oxide capacitor here and a semiconductor capacitor here. So we have an oxide capacitance in series the semiconductor capacitance. What is the semiconductor capacitance? That depends on where you're operating, but essentially there is a semiconductor capacitance. Okay, this is the correct option. The semiconductor capacitance will depend naturally on the gate bias, which regime you are operating in. We'll come to this concept again. Okay, but here I am just qualitatively saying that this is the complete picture. You can break this whole system into two different capacitances, Cox, which will not change, because remember, epsilon oxide is fixed. Once you have chosen the material to fabricate this capacitor, Tox is fixed and area is fixed. So Cox will remain constant throughout. Semiconductor capacitance will vary depending on the gate bias. Okay, so please recall, the question can be asked in different formats. For instance, MOSCAP can be represented as series combination of two capacitors. oxide capacitor as semiconductor capacitor. Which of these capacitors will vary according to gate bias? So oxide capacitance will not vary, it will remain fixed. However, semiconductor capacitance can vary. We'll see when we talk about the low frequency CV and high frequency CV curves. Okay, right. So next problem, in a SiO to Si interface, how is the electric field on the oxide side related to the electric field on the semiconductor side? Okay, so let me draw the diagram again. We have the metal, we have the oxide, and we have the semiconductor. This is, they're saying x equal to 0, and x equal to 0 minus is the oxide, so this means this is the x-axis. So we are essentially have to apply the boundary condition over here, right? What is the boundary condition? If you recall that epsilon 1 E1 minus epsilon 2 E2 equal to Q. Look at this interface. Epsilon 1 E1 equal to Q, what is called Q enclosed. This is from electrostatics. Epsilon 1 is, let's say, oxide. This is oxide. This is semiconductors. And remember, one of the assumptions that we have made, there are no trap charges at this interface. So Q enclosed has to be 0, right? This will be epsilon ox, electric field on the oxide, minus epsilon silicon, electric field of on the silicon side, right? So take it to the other side, epsilon eox equal to epsilon silicon times electric field on the silicon side, right? So let's see, what we do know is that epsilon ox is around, let's say, 4, and epsilon silicon, let's say for the sake of discussion, 10. Okay, so what's going to happen is that electric field on the oxide side will be 2.5 times electric field on the silicon, right? So electric field on the oxide side is larger than the electric field on the semiconductor side. This option. Very straightforward. I mean, just nothing. It's just I'm applying simple electrostatics. And what happens is that in reality there is some charge, some trap charges that are here, which we try to minimize, because then this balance will vary. And this is very important. We need to know these values to a reasonable degree of certainty in order to operate our devices. Okay, so in the next we have again a metal, yeah, so this is again an MOS. We have your metal gate or metal, we have the oxide, and we have the semiconductor. Here, what is the oxide? Oxide is nothing but hafnium oxide in this case, HFO2. What is the semiconductor? Semiconductor is gallium nitride. Remember, we had talked about this in context of LEDs. It's a direct band gap semiconductor. So semiconductor is gallium nitride. Again, this is a metal oxide semiconductor capacitor. So the electric field strength in the oxide. So we had already, again, we'll assume no trap charges here, and we had seen that epsilon ox electric field oxide equal to epsilon gallium nitride electric field of gallium nitride. Yeah, so dielectric constant of gallium nitride is 8, which is given. Electric field of oxide, epsilon of oxide is 16, right? So what we have is now that we have to find the ratio of oxide to gallium nitride. So E ox on E gan will be 8 by 16, which is 0.5. This one. In the previous session, you remember this entity was 2.5, right? So there, in this case, the most of the electric field, right, is dropping across gallium nitride, the semiconductor that we have. Most of the electric field is dropping here, not here. In the previous case, see, electric field oxide was 2.5 times of silicon. So here the electric field was dropping here. Electric field dropping in oxide. More electric field dropping in oxide. Usually we have moved to high K materials. Another problem which we'll visit, and there I'll have a more discussion on that. But this is just to illustrate that how the basic electrostatics is playing a role in these circumstances. Okay, now we need to identify the maximum width of surface depletion region. This is again, we have a MOSCAP. We are given so please remember, we are given now Na. So what we have given is a p-type silicon. This means we can form n MOSCAP with electrons as inversion charge or inversion layer. What will be the depletion width? This is the expression that you have from your Schottky contacts. Just please refer to that, and yeah, so we'll be fine with that. So what we have is now okay, so maximum width of the surface depletion region of a MOSCAP with these entities. So let me just put these numbers. Epsilon naught is 8.85 10 to the power minus 14. Epsilon silicon is 12. Phi s is something we need to identify, right? This phi s is essentially is nothing but your 2 phi f. That's when the inversion will start, right? That's when the depletion region will stop extending, and it will stop, and all the charge will be accumulating in the all the charge, whatever is happening, will be happening in your on the oxide interface itself. Q and ND here it's Na, it's 10 to the power 15. So phi s is nothing but 2 phi f, and phi f, if you remember, was dependent on doping. So how do we identify that? We say that P equal to NV. Phi f is essentially actually was your EI minus EF. Okay, and exponent of EV minus EF over KT. It can also be written as Ni exponential of this is nothing but your phi f. So phi f, you can calculate it from here. It will be KT by Q ln. Concentration of holes in bulk will be nothing but Na over Ni. Find this value of phi f. Phi s is 2 phi f. You put it here, and to do some calculations, it will be around 0.8, 0.9 microns. Okay, I'm just telling you what is happening. So why phi s equal to 2 phi f? Again, because that's the condition for strong inversion. After this, whatever you do, whatever extra things, whatever extra charge you're putting, it will not extend the depletion region. It will just put more charge at the interface itself. Remember that that diagram that we had drawn earlier. So this is the Q versus X. This is your metal side. Here it's your, this is your plus, this is your charge. This is your gate charge plus Q, right? And this was your depletion charge, and this was your inversion charge. So after depletion, after inversion has formed, all the extra charge will be coming only on the inversion layer. Depletion region will not extend, it will stop. Okay, and we are required to determine this problem where it will stop. So it will stop when you are entering the strong inversion. As simple as that. We just put these numbers, and you can easily get the answer which I have obtained here. The expression is similar to what you had in your Schottky contact, or in a, let's say, in a P plus N junction, because one side is heavily doped, right? Only one side we are talking about here, the P side semiconductor in this case. Okay, now I have a series of questions in which we need to analyze, we need to identify what is the threshold voltage. I have not introduced the term the threshold voltage yet. So threshold voltage is essentially the voltage, so VTH is when you are entering the inversion. Okay, so VTH is formally defined as, let me just give me a second. I don't want to be wrong here. Yeah, QD by Cox plus 2 phi f. Okay. This is the threshold voltage. Again, remember, I'm assuming the ideal case. That goes without saying. QD is a depletion charge. Cox is your oxide capacitance. So essentially, what is the threshold voltage? Threshold voltage is the voltage that you have to apply at the gate to enter strong inversion. So this is all the band bending that is happening. So first you have to apply a charge to cause depletion, which is this Q equal to CV, as simple as that. QD is a depletion charge. Q times V, Cox times VTH. Essentially, this much potential you have to apply, plus you have to apply an extra potential to cause inversion. This is very straightforward expression. This term comes because you have to invert. This term comes because we have to deplete. Simple. Now, in this problem, we are given two MOSCAPs, both on p-type substrate. So p-type substrate will give rise to NMOS. So A and B, the difference is between their doping. And NDA is 5 into 10 to the power 16, and NDB is 5 into 10 to the power 18. Alright. Assuming the same metal semiconductor work function difference, so that is the phi ms. Again, we are assuming that's non-existent here. And oxide thickness. So oxide is not playing a role. Okay. Let's see. We'll try to talk about each of these terms in order to arrive at as to what I am saying. Okay. So the thing that is changing is the doping. Okay. So let's just change the doping. That how does the QD will depend on doping. Okay. So QD is nothing but a depletion charge, right? Depletion charge will depend on how much you have doped it. Simple as that. Because this is per unit volume, let's say. Okay. This is per unit area rather, because QD will be per unit area. Cox is also per unit area. It also, we have normalized with respect to area. QD will essentially your coulombs, right? And Cox then has to be in terms of farad, right? So epsilon A by D, epsilon ox A by D. Cox will be epsilon ox A by Tox. This is same for both, because it's given Tox is the same and SiO2 is the same. We are assuming same for both. QD is your total let's say charge that is there inside the depletion region. So that will depend on your doping times area times depletion width, right? Because this is per centimeter cube, and this everything has to be coulombs, right? So Na times A times W. So what is different here? Na is what is different in both the cases, and correspondingly, if you see W, the depletion width, if you recall the expression that is written over here, that is again dependent on phi s and Nd, right? So let me just write it here. Na times A times 2 epsilon naught epsilon s phi s over Q times Na. Okay. Phi s is nothing but your 2 phi f. Please remember that. So then we need to first analyze how it's dependent on phi f, because then only we'll be able to determine about the QD, right? So let's analyze phi f first. Phi f, which is nothing but your EI minus EF in bulk, right? And we have already derived an expression. Yeah, this is this KT by Q ln Na by Ni. So phi f will be more for, so phi f for B will be more than phi f for A, because doping is higher. You can clearly see for B it's higher. Okay, if phi f is higher, and we know phi s is nothing but 2 phi f, so this term will be higher, right? And you can also say area will be the area is there. So what will this be? This will be 2 epsilon naught epsilon s into 2 phi f times Na, this 1 square root will get cancelled out, into, let's say, a squared over q. Now for qd in B will be higher than qd in A. Why? Because phi f is higher first of all in B, and Na, the doping, is higher in B as well. It's 5 into 10 to the power 18, 2 orders higher. So this term will also be higher. Correct? Right. So what we can see is that qd term is higher, right? And your phi f term is also higher in context of your yeah, okay. And one more thing, this qd is negative, by the way. This minus qd that I have written, please remember, if you recall that diagram, charge versus x. So this was the gate, right? And here we had, this was the oxide, right? This was the oxide, and here is the semiconductor, and this was the inversion charge, and here we had the depletion charge. This is negative. So this qd just denotes that so essentially VTH will something come out to be positive. Please remember, we have to apply a positive charge, right? So here I'm talking about the magnitude of qd rather, and so minus qd will be a positive entity. So a qd for B is higher and phi f for B is higher, then naturally VTH for B will also be higher, because qd, you have to deplete more, essentially you have to deplete more charge because the doping is higher, and phi f is higher, so you have to bend much more. Okay, these are the simple, and these are the two simple reasons for which VTH, the threshold voltage for MOSCAP B, will be higher. So this will be a correct option. Okay, this is the analysis that we had done, because VTH depends on inversion charge, the band bending and the depletion charge. Depletion charge is higher when we have more doping, because you have more to deplete, essentially, as simple as that, right? And your phi f is higher because your bending is also higher. Now phi f is higher because your Na is high, essentially. Okay, and the second problem that we have is similar thing, but now what we have is, I'll again write VTH is minus qd over Cox plus 2 phi f threshold voltage. This time we are changing the gate metal. Okay, so 2 phi f will not change, because remember, this depends on doping. And qd, Cox will also not change, because epsilon ox Tox will also remain the same. qd is nothing but your depletion charge, that will also not change, because you saw it depends on doping in area and whatnot. So you'll assume that nothing will change here. No, something will change, because please remember, now phi ms, we have assumed phi m equal to phi s throughout this. This is not the case anymore, right? So whichever has, so essentially the modified expression of VTH will look something like this. This term is due to metal semiconductor work function difference. So phi m for gold, I think, let me just check, I have it somewhere. So for gold it's 5.1, for aluminium it's 4.1 eV. Okay, and for that matter I also have to check for silicon, the work function of silicon, right? Because then only we will be able to determine the difference between them, right? So just give me a second. Work function of silicon. Work function of silicon is 4.9, let's say. Work function of silicon is 4.9 eV. Okay, so what we see is that phi ms for A will be equal to 5.1 minus 4.9, which is 0.2 eV. This term I'm not even worried about. All right, and phi ms for B will be 4.1 minus 4.9, which is minus 0.8 eV. This entity, whatever it is, it will be a constant. So you can see that the VTH for A will be this entity plus 0.2. Let's say this quantity is 0.8 eV, 0.8 volts. Okay, so what will the VTH for A? VTH for A will be 0.2 plus 0.8 will be 1 volts. VTH for B will be minus 0.8 plus 0.8 equal to 0 volts. So you can say VTH A is higher than VTH B, right? This is the correct option. Again, these two entities for this problem will not matter because these are dependent on the oxide and semiconductor, not on the metal. The metal term will come only for phi ms, and since phi ms is higher for gold silicon as compared to aluminum silicon, so this term enters over here. This is essentially to arrive at the flat band. We'll come to this in the latter part of today. Okay, the third problem we have now, similar thing. Just now what we have done is now we are changing the gate dielectric. So again, VTH is minus QD by Cox plus 2 phi f. So 2 phi f will depend on doping essentially, so this will not change. QD is the depletion charge, that will also not change. The only thing that will change is Cox, right? So let's determine Cox1. Cox1 will be epsilon ox1 A1 over T1, and Cox2 Cox, yeah, let's call them A and B. Cox B will be epsilon ox B times area of B over thickness of B. I'm assuming that their area and thickness are the same for both cases. So what will it be? So Cox of A, what is it? Material A? A is aluminum oxide. So aluminum oxide, I guess something as 10 A by T, and Cox of B will be, this is 4, silicon dioxide is 4, right? So how will the VTH of A will change? So remember, this is a positive quantity. QD is depletion charge in itself is negative. We are talking about NMOS here. Okay, so this is essentially negative quantity, so this whole term comes out to be positive. So VTH A, let's say VTH A minus 2 phi f, this magnitude will come out to be QD, put the value of Cox over here, 10 A by T, and VTH B minus 2 phi f, its magnitude will come out to be QD into T over 4A, right? If I'm considering only in the magnitudes, so VTH A will be 2 phi f plus mod QDT by A over 10, and VTH B will be 2 phi f plus mod QDT by A by 4. So what's happening, this entity is being divided by 10, and here divided only by 4, so naturally this term will be higher. QDT by A will be some positive quantity. Okay, let's say it's 40, I'll not say 40, let's say it's 4. Okay, to make our life simpler, let's say it's 4, and 2 phi f is let's say 1 volts. So this will be 1 plus 4 by 10, this will be 1 plus 4 by 4, so this will be 2 volts, this will be 1.4 volts. So as you can see that threshold voltage of B is higher. Simple. Essentially what is happening is that your Cox has changed. So when a capacitance of the oxide has changed, now your this is essentially the electric field lines, right? So we remember we had done an exercise in epsilon ox E ox equal to epsilon silicon T silicon E silicon, right? So if there are more electric energy is being stored inside the oxide capacitor, less will be stored inside the semiconductor capacitor. We had seen that those capacitors are in series. Essentially it's coming from that effect, electrostatically how the energy is being distributed. Okay, mathematically this is the course. Finally, the fourth problem that we have in this, what we have is the things are changing based on your thickness of the semiconductor. So you see, everything else remain the same, doping, function, and on one side we have 1 nanometer gate dielectric, another we have 10 nanometer gate dielectric. Again, this comes from doping, so this will not change. QD will not change again. Cox will again change. So Cox A will be epsilon A, area A over TA, and Cox B will be epsilon A epsilon B area B over TB. So so this remains the same, epsilon A over, what is the thickness? Thickness on the first case is 1 nanometer, and other case it's 10 nanometers. Okay, again you get the magnitude of this. This will be 2 phi f plus QD TA over epsilon A, area of A, magnitude of this. And similarly VTHB is your 2 phi f plus QD TB over epsilon B, area of B, right? Again, I'll assume, let's say 2 phi f is 1 volts, okay, plus this whole entity QD over epsilon A into area of A is, let's say, 1 nanometer inverse. Okay, so this will turn out to be 1 times 1. Here it's again 1 volts plus 1 times TB, which is 10. Actually, it's a very bad example. Let's take them to be 0.1. So 0.1 times 1, and here it will be 0.1 times 10. I'm just putting some number just to make our life simpler. So 1 volts plus 0.1 volts, this will be 1.1 volts. This will be 1 volts plus 1 volts equal to 2 volts. So again, threshold capacitance VTH for B is higher. Again, why this is changing? Nothing else is changing. It's just because we have changed the technology. We have moved from a 350 nanometer or the old technology to a newer technology, which is 45 nanometer technology node. What changes is the gate length, oxide thickness. If the oxide thickness changes, we can clearly see everything else remaining the same. Now the VTH has also reduced quite a bit, from, in this case, 2 to 1.1. These are just some hypothetical numbers, but whatever values you choose, you can still see them to be decreasing. Threshold voltage decrease, and this actually creates a problems, because every time these capacitors, which and in fact the MOSFETs which are made on them, are actually used in switching circuits. If the VTH is very low, a MOSFET can be turned on and off just by some random noise. So these are some peculiar things that we have to that the engineers have to take care of. And also, when you are operating with 1 nanometer thickness oxide, we have already talked about this tunneling. The electrons can simply tunnel through, because this is 1 nanometer, is a very thin. This is just only a handful of layers of your silicon dioxide. Okay, so there are ways to fix that by using high K dielectric and whatnot. So yeah, that's that. Okay, so how much time do we have? Okay, we have half an hour. Fine. So now we talk about one of the core rather studies in MOSCAP is called the CV characteristics. So you have your metal oxide semiconductor stack. You can see that I have not applied it any bias. So what will have? It will simply add its flat band. Again, I am assuming phi m equal to phi s, and this is a p-type semiconductor, as you can see, because EF is closer to EV in the bulk. Okay. Now let's apply some positive bias. Okay. If you apply some, we'll apply some bias. Okay. And let's say this value of Vg, in this case applied bias, is negative. We have already seen that what happens when it's negative. So when you apply a negative bias, it will attract the holes and it will cause the accumulation. And this is how the charge profile looks like. You're applying a negative bias at the gate. So this is the minus Q. So this is your metal side, this is your oxide, this is your semiconductor. Okay, and the holes will get accumulated on the other face of the oxide layer, right? Okay, and then what we do, I am applying a very small bias, an AC bias with voltage of the magnitude Vs. the frequency omega. So what's going to happen is that something like that will happen. There'll be a change in charge denoted by this delta q. This delta q directly corresponds to the change in the voltage, that the AC voltage that is fluctuating. Okay, the DC will not change. DC is given by VC. So essentially that's to say Vs is small. Okay, Vs is small. This means as compared to Vg, the change will be only minimal, which is denoted by these black squares. Okay, so now I need you to recall your q equal to CV you have, right? So this expression C equal to dq over dV. So we are assuming this, changing this delta q, changing this voltage, and what is the result? Some current, this charge is changing. Where is the charge changing? Charge is changing across the oxide capacitance. This is the oxide. So what will the capacitance? Capacitance will simply, capacitance in the accumulation, we are talking about the accumulation, will simply be nothing but Cox, because that's where the charge is changing. Okay, C accumulation will be equal to Cox. How do I draw this? So I draw x-axis I have Vg. Remember, this is the CV characteristics, capacitor's voltage. X-axis I have Vg, y-axis I have capacitance. I have normalized with respect to oxide. So C by Cox. So it is a C accumulation. In the x-axis it will be 1. Sorry, it will be something like this. This line is C by Cox equal to 1. This line. This is unity. Alright? Fine. Now let's talk about the second case. We have flat band. I'll apply some voltage. What voltage this time? Slightly positive voltage. So it will repel away the holes, and which we enter, called the depletion node. At the surface it's still intrinsic, it's not inverted yet. Okay, in the bulk it's p-type, but on the surface it's still slightly p-type or intrinsic. So we are operating in what we know as the depletion region. The negative charges will be fixed over here. Okay, again then I apply a small AC bias to that. What will happen? The charge will modulate like this. The depletion width will fluctuate, right, depending on the magnitude of polarity of Vs. And essentially you get these small black squares. Again, you recall that C equal to dq over dV, right? So where is the charge being added? Charge is being added to the depletion layer. So what capacitance is changing? Depletion capacitance is changing. And total capacitance is nothing but, we have talked about, this is oxide, this is semiconductor, silicon, and this is metal. C is Cox, parallel C, because this is in series, right? These are in series. So 1 by C will be 1 by Cox plus 1 by C dub. Cox will remain constant, epsilon A by Tox, that remains same, but C depletion will change, right? C depletion is your epsilon silicon, area silicon by thickness, right? Epsilon A by T, and you can see that it's the T that is changing, this dimension. This is what that's changing. So it will be epsilon A by epsilon silicon A by W, the depletion width that we have. Okay, we have already seen C by Cox equal to 1. This is in the accumulation. You can see Vg is negative in this side. So this is for accumulation. How will this look like in the depletion? So first Vg is positive, you can see. So we'll operate, let's say, in this region somewhat. Okay, this region we have to plot it, and as you increase Vg, as you increase your Vg, your depletion width will increase. You notice that. DC case, in this case, you increase Vg, more and more holes will be repelled away, depletion width will increase. If your depletion width increase, so I can write this as Vg increases, W increases, and C depth decreases. Because C depth is what? Epsilon silicon area by W. W increases, your C depth decreases. If your C depth decreases, the whole capacitance will also decrease. Okay, so what you see is that you see this kind of a curve. It's not a straight line, it's a curve actually. Something like this. Okay, We have talked about depletion now. Let's go to accumulation. We have flat band. We'll apply some bias, this time highly negative bias. Sorry, a highly positive bias. We are in depletion, right? And now I apply the bias even further. So now we have entered the inversion. You can see that. And the bulk EF is closer to EV on P type. However, at the surface, EF is closer to EC. This is EI. This is EC. This is the surface I'm talking about. So the material has been inverted, okay, and this is how the charge profile looks like. So this is your depletion, the red, and the green that you see is your accumulation charge. Okay, again what I'll do, I'll apply a small AC bias. How will it happen? So if I have a small frequency of this AC bias, okay, low frequency, that means now what can happen is that now the electrons which are in the system now they can have time, which are in this layer in the bulk, they'll have time now to travel to the surface and get collected over here. They can reside over here. However, so this was the graph that I had earlier. Now what will the capacitance here? So capacitance, where is the charge changing? Charge is changing only across Cox. So I can write that C inversion will be equal to Cox, because only across oxide the charge is changing. Okay, so so how will it look like? Cox is this. We have to see by Cox is 1. So I will go something like this. This is your LFCV, low frequency CV. However, if I change it very fast, this frequency is very high, the electrons will not get time to come to the interface. Only the depletion width will have to increase then. So the depletion width increases, and we know that in this case C inversion will be Cox in parallel with C depletion. And C depletion, we have already seen the previous slide, will depend as inversely proportional to W, right? So what will happen in that case is that this slightly decreases. I mean, I'm not able to show it here. Maybe, yeah. So I have that plot already. So this is how the nature will look like. So LFCV, since inversion capacitance is Cox, it will go like this. This more or less flatlines because the change in actually W is not that significant. That's why it kind of saturates it in high frequency CV. Okay, the basic between these two curves happens only after the inversion, because the inversion charge for low frequency, the electrons get sufficient time to come to the oxide semiconductor interface and reside, either come here or go away from there depending on the polarity of the AC voltage. In this case, that is not the case. So it's a depletion width there has to be altered for high frequency CV. Okay, and this is a very famous curve for the CV characteristic. This is very extensively used for to identify the nature, for instance, to identify VTH, the nature of the material, how close it is to ideality, and so on. This entity is also known as Cmin, by the way. So where your depletion width ceases to increase. Okay, just these entities is some important numbers that you must keep into account, that you must keep in your mind. Okay, how much time do we have? Okay, 15 minutes. We should be fine. Okay, so in this problem, in a typical MOS capacitor, high frequency capacitance, MOS capacitance, is less than low frequency capacitance in which regions of operations? So we had just talked about this. So this is C versus V. I'm going to draw that again. So this was the accumulation region. I'm talking about here an NMOS. So let me first draw this. So this is your metal or gate. This is the metal, and you have your oxide here, and you have your semiconductor here, let's say P type, grounded. Okay, so this is the accumulation. So this is Vg, which is negative. The value here is capacitance equal to Cox, and then we entered it. If we apply positive Vg, we entered into the depletion region. Looks something like this. You arrive at this, which is something called the Cmin, right? And if you have low frequency, this means that the electrons will get sufficient time to come to this interface, right? And thus the only capacitance which will be seen is the Cox. So for LFCV, this is how it will look like. For HFCV, we have seen that it looks something like this, right? And now let me mark the different regions again for this. So this was the I've written here accumulation, depletion, and this region is inversion. So as you can see, LFCV and HFCV are the same in accumulation and depletion region, right? Where do they differ? They differ only in the inversion region. So this will be the correct answer. And HFCV is lower. So that HFCV capacitance is less than LFCV capacitance in the inversion layer only. So option C will be the correct answer. Okay. Right. So as I had talked about earlier, that I will try now breaking one or two of these assumptions that we had. Okay, so this is from your, I think, the first slide for the MOS capacitor today, where I taken some assumptions that metal semiconductor Fermi levels are the same, and we've already seen one problem where we had, for instance, that where we compared the VTH of aluminum and gold, right? And we saw, I brought this. I will again talk about this. Second assumption that will break is this one, that there are no traps at semiconductor inside oxide interface and within the oxide. So I'll try to break the second part of this assumption. Okay, so let's see it now. Now you can see phi m minus phi s is not equal to 0. So this is some vacuum level, let's say over here. So this is your phi m and this is your phi s. Clearly you can see they are not aligned, right? So since the electronic energies are different, when you bring these, so till now they're not touching the metal. This gray is your oxide and this band diagram is for semiconductor. When you touch them together, you can clearly see the EF has to remain the same when you're not applying any bias, and but you will see something like this. So but you can see that even when Vg equal to 0, this means an equilibrium, EF is flat. That's the definition of the equilibrium, but you can still see some band bending. And all the analysis that we have performed till now, we first bring the system to flat band and then we apply Vg less than 0, greater than 0 and whatnot. Okay, so same thing which we'll do, we'll try to apply such a bias to this gate. If we apply a phi ms to this gate, right? If we apply a phi ms, if we raise Vg by phi ms amount, what you can have is you will have a flat band again. You can see that the bands have become flat. Now you'll say it's not it's not an equilibrium, we know that, but if we add phi ms extra, if we add this offset, we have arrived at the flat band condition. Now all the analysis that we had done for accumulation, depletion and inversion will stand valid. All that physics that we had discussed will still be valid, because that physics we had discussed was for a model, was for a semiconductor oxide interface which was in a flat band condition. Please understand. So hence we first have to bring the system to flat band. Okay, so I'll say it like this. 1 second. First bring the system to flat band regime. How? By applying this VGS. By applying Vg equal to phi ms. And phi ms is relatively straightforward to determine. You know what metal you are depositing over here. You know the semiconductor. So this is not too difficult to identify. In practice there are some problems, but yes, at least you have a starting point to identify. Now we have the flat band and now all the analysis remains valid. So this was the expression for VTH ideal. You simply add phi ms to that term, because we first have brought it to flat band. To bring it to flat band, we applied phi ms. Hence this phi ms term is added, and this becomes now your expression for VTH. As simple as that. So we already talked about this term comes from the depletion. This comes from the band bending. So those two terms remain as it is. The only, because this analysis was based on whatever we had talked about, the physics of the band bending and why two term comes here and the depletion happening. This phi ms is just the extra offset term, so you can that's how I tend to imagine it. Okay, so this is the first non-ideality in a MOSCAP. The second non-ideality is that you can have some oxide charges. So you can see this is the oxide layer, right? You also have EFM not aligned with EF of this. So in this case I have both phi ms is non-zero, as well as you have some oxide charges. Now what will happen is that when you bring the system together, you'll have some band bending because your energies are different on both the sides. This plus charge essentially is your electric field, so to speak, or you can say it has some electrical energy to it, right? And you can see some corresponding Fermi level is denoted by, if you can see this mark here, right? So it will have some flat band. Again, we don't want that, right? So how to compensate for that? Again, you apply some phi ms, right? So what we'll do, apply some Vg to compensate for band bending. Now how much to apply? Phi ms we have already seen, and then you apply this much amount of voltage. Why this much amount of voltage? Because we know Qi is essentially your trap charge, trapped oxide charge by Cox. Usually this is positive in nature, and hence this term will be negative, because you're compensating for a positive charge, you have to apply negative potential. So Cox is nothing but the oxide capacitance. So now if you apply this much of potential to Vg, you have arrived at a flat band condition. Once you have arrived at a flat band condition, now again your analysis, so this was your VTH ideal, right? This term comes from your band bending, this term comes from your depletion, and the first two terms are coming from non-idealities. This is from work function difference, and this term from oxide trap charges. So these are the two non-idealities that we can think of breaking, and these are very straightforward. There are other complexities involved. For instance, these trapped oxide charges are sometimes not so straightforward to determine, but from at this level, I believe that this is, at least you can appreciate that why am I compensating for these two terms in such a fashion. Okay, so we have already seen a problem for phi ms. Yeah, so this entity now in the blue square that you see is also known as, by the way, by the flat band voltage. This means that in order to bring the system to flat band condition, what gate voltage should you apply? Okay, this much voltage you should apply just to arrive at the flat band condition. This is also known as VFB. This is a problem that can be asked, a numerical problem that can be asked in your assignments, competitive exams and whatnot. So please try to recall this entity. This negative sign is primarily because the trapped oxide charges, silicon oxide, are predominantly positive in nature. Hence, this term, this negative sign comes due to that effect. Okay, so 1 second. Okay, so I'm sorry that the answers are here itself. I forgot to remove them, but anyways, we can still try to solve it. So consider a MOSCAP with p-type substrate doping. Which of the following statements are true? Second. Okay, see, good. So okay, so first let me write the expression for VTH. VTH is phi ms minus Qi by Cox plus, let's say, some VTH ideal. Okay, and I'm ignoring phi ms here, so let's not worry about that. Okay, so VTH will be equal to VTH ideal minus Qi by Cox. Okay, so that's fine, but how does it depend on CV? So this CV, first of all, I'm drawing is for ideal. LFCV and HFCV, right? So, and somewhere over here lies, let's say, VTH. This entity is VTH ideal. Now, if Qi is positive in nature, right? If Qi is positive in nature, you can see this whole entity will shift to the left. VTH will be less than VTH ideal, right? So let me draw it with the blue color. How will it look like? It will look something like this. So this curve belongs to positive fixed charge.